In this video, we're going to start to take a look at how we can go back and forth between our two coordinate systems. So I'm going to just draw up here my x and y axis. That's my frame of reference for rectangular coordinates. And then I'm going to overlap with that my frame of reference for the polar coordinate system. So I'll put the pole at the origin and the polar axis on the positive x-axis. And I'm just going to draw a point, which I'm going to call P. Now I've chosen very consciously to put that in quadrant 1, because quadrant 1 is the simplest. In quadrant 1, x and y are positive, and it's possible to land in quadrant 1 using an acute angle. Okay, so this point P would have rectangular coordinates, and those are unique. It would have polar coordinates, r and theta, which would not be unique. But what I'm going to do is draw a picture of the rectangular coordinates and the simplest choice for polar coordinates. And that means I'm going to draw this lovely right triangle right here. Okay. X and y would be the legs, because to get to point P, I'm going over x and up y. Now in quadrant 1, x and y are both positive, and so they are legitimate side lengths. In other quadrants, at least one of x or y is negative, so I would just have to interpret them as signed side lengths, and that's fine. Okay. Now, my simplest choice for r is to let r be positive. So r would just be the distance from this point to the origin. How convenient, that's the hypotenuse. And the simplest choice for theta, in this case, would just be this acute angle right here. Okay. Now, I'm going to use this triangle to derive some formulas. And if we're careful, we'll be able to derive formulas that will be valid not just in quadrant 1, but for any point on the plane. And not just for the simplest choice of polar coordinates, but for any choice of polar coordinates. Okay. Now, I'm going to start by trying to describe x and y in terms of the polar coordinates r and theta. I'm starting with that because x and y are unique, so I should expect to be able to get explicit formulas that spit out the exact right answer. I'm not going to expect that when I'm describing r and theta because they're not unique. So I can look for an equation that gives me a relationship between r and x and y, and between theta and x and y, but I can't necessarily expect that I'll be able to solve r must be this, because that would take away the choice. I've got options. Okay. So if I'm trying to find a relationship with x and I want to describe it in terms of my r and my theta, notice I've got this angle, the adjacent side, and the hypotenuse. I'm thinking cosine. So cosine of theta is equal to x over r. Well, that's going to mean that x is r cosine theta. And it turns out that always works. It works regardless of where my point is. So it works in every quadrant, and it works for points on the axes. Okay. And it works regardless of the choice that I make for r and theta. So this triangle doesn't prove it, because this triangle supposes that we're in quadrant 1, so that x and y are positive, and that r is positive, and theta is acute. But I'm simply telling you this formula works in all cases. And you can sort of play around with it. Say, what if I had a point in quadrant 2? If I chose r to be positive, theta would land in quadrant 2 as well. Well, that makes sense, because in quadrant 2, the x value is negative and cosine is negative, because cosine is associated with the capital X value where I intersect the unit circle. Okay. If I were in quadrant 2 and I chose r to be negative, well, then theta would have to land in quadrant 3. Okay. Then cosine would be positive, but I'd be multiplying that by a negative r value. I'd still get that x was negative. Okay. So you can sort of play around with it. Notice, if I wanted to describe this point P with a negative r, I'd have to choose an angle that landed in quadrant 3, but the reference angle for that would actually be the same as this acute angle. Okay. All right, so I didn't full-on prove by going through every single possible scenario that this always works, but you can sort of play around with it, and it makes sense. but this is a really nice way for remembering it. Okay, let's do it for y now. Y is the opposite side. So sine of theta is y over r, and that means that y is r sine theta. And again, it turns out that that always works regardless of where my point is and regardless of which pair of polar coordinates I choose to describe it. Very cool. Okay, let's look now at what if I wanted to describe my polar coordinates in terms of my rectangular ones. So let's say I want to describe r in terms of x and y. Well, that's just the three sides of my triangle, so I'm thinking Pythagoras. X squared plus y squared is r squared. That's always true. Now, r can be positive or negative, so I can't solve uniquely for r. I can get it down to two choices. R will be plus or minus the square root of x squared plus y squared. Okay. And of course, whether I choose the positive or the negative, that choice has to go hand in hand with my choice of theta. If I choose r to be positive, which I usually do because it's simpler, I'm going to choose theta to land in the same quadrant as the point. If I choose r to be negative, I would have to choose theta to land in the diagonally opposite quadrant. Okay, let's now take a look at theta, which I managed to erase. Okay. If I want to describe theta in terms of the rectangular coordinates x and y, that's my angle, my opposite, and my adjacent. Tangent of theta is y over x. Now do be careful. It's tempting to try to solve for theta, and we can't. Arctan of theta would, arctan of y over x, not arctan of theta. Theta would be, in some cases, arctan of y over x. But that only works if theta is in the range of arctan. That would mean I'm only allowed to choose angles between negative pi over 2 and pi over 2. But I might have a point on the y-axis where theta would need to be pi over 2 or negative pi over 2 or something coterminal with one of those. I might want to describe things with an angle that lands in quadrants 3 or 4. There are no restrictions on what theta is allowed to be, so I can't describe it in terms of arctan because that would impose some restrictions that simply don't apply. So when I'm trying to describe r and theta in terms of x and y, I can get r down to two possibilities. This is as far as I can go with solving for theta, but then what I can do is I can say, let's use the sign of x, y, and r to figure out what quadrant we're in. Okay. And then I can pick a theta that lands in that quadrant that has that tangent. Okay. So I've got to do a little bit more thinking when I'm working with that. So I think what we'll do right now is let's practice using these simpler formulas that give us a unique answer. And then as we move on, we'll build our way up to finding multiple options for polar coordinates. So let's just say that I had r theta is equal to negative 2, negative 3 pi over 4. And I want to find x and y. I'm going to start out by just doing it geometrically, not referring to memorized formulas, but just figuring it out from a graph. And then I'll point out that if I preferred, I could just plug right into these formulas. So let's take a look. If I were going to be plotting this point, okay, so negative 3 pi over 4 is going to look something like this. Okay, so that's the positive direction, and that would make this the negative direction. Okay. Now, because I'm going in the negative direction, a distance of 2, my point's going to land up here somewhere. And what I know is just labeling that distance, that's 2. Now the r value is negative 2, but here I'm labeling the actual distance, 2. That would be the hypotenuse of this triangle. I can also figure out what this angle is. Because if this is negative 3 pi over 4, the reference angle here would be pi over 4. But we know when intersecting lines meet, these angles that they form, these angles that are on opposite sides of each other, are actually called vertical angles. They're the same. So that's pi over 4. Very cool. Now, I know that my usual triangle with a 45, 45, 90 would be 1, 1, root 2. I can see I've just drawn a scale model of that. Basically, in order to bump this up to 2, I had to multiply it by root 2. So let's multiply these sides by root 2 as well. And of course, they're both going to be positive because we're going right and up. So xy would equal root 2, comma, root 2. Okay. Now, I could also have gotten that just from here. I could have said x is r cosine theta. That would be negative 2 times cosine of negative 3 pi over 4. So that's going to be negative 2. And here, this is going to be a two-step process. Negative 3 pi over 4 lands here in quadrant 3, where cosine is negative. I'm going to attach to that the cosine of the reference angle, which is pi over 4. So that would be root 2 over 2. So notice the negative times the negative cancels, the 2's cancel, and I get root 2 for my x value. And I could do the same thing for my y value, just plug directly into this formula. Okay. I kind of like, even if I am going to use the formulas, I kind of like to have the picture so I can sort of double check. If I plot the point, it lands in quadrant 1, I feel good about x and y both turning out to be positive. So I kind of like to use that as a double check. All right, what I'm going to do is give you some polar coordinates, and before you start the next video, I want you to find the rectangular coordinates. And again, you can do it by just drawing the picture and figuring things out using right triangle trigonometry, or you can use these formulas, or you can do a combination of the two. Okay. Let's suppose that r theta is 3, 5 pi over 6. Okay. So, before you start the next video, see if you can figure out for me what x, y are. All right, see you soon.